Hello, our project is AI image classifier, learning to identify AI generated images and faces using binary image classification. My name is Taisei.
My name is Tyler.
I'm Joshua.
I'm Daniel.
I'm Antonio.
And we'll be going over the introduction.
So the first thing to go over is what an AI image classifier is. And to begin with, just some context. There's been an uptick in image generation technology. So the advent of new models like DALL-E and ChatGPT are able to produce more and more realistic images based on user prompts. And this makes distinguishing AI generated content from real content increasingly challenging and necessary. So the potential risks that comes with these new AI generated images are erosion in trust in digital media, potential identity theft, and rise of misinformation. So the solution we are proposing is an AI image classifier. So this is a binary image classifier based on a convolution neural network to classify images either real or AI generated. And we train the model using a labeled dataset from Kaggle. So just some more background information on the related work. So firstly, binary image classification is a type of categorization that labels images as either labels between two groups. In our case, this is real and machine generated images. So for this, we're using a deep learning model, as deep learning models are preferred because they have the ability to learn detailed features through complex structures. And our specific model is a convolution neural network, also known as CNN. And CNNs are highly effective and widely used for binary image classification. They're trained using large data sets and have sophisticated deep learning techniques to improve classification accuracy.
All right, so each branch of our project has its own data set. The images use vary in size, but they're all resized to a resolution of 224 by 224 when training. The image classification branch has a data set of over 174,000 images, and it's split with roughly 92,000 real images, which consist of authentic photographs of landscapes, cities, animals, or portraits, as shown on the right. And the remaining 82,000 images, also very content, but they're all AI artistic renderings. And moving on to the face classification branch, we used a data set with exactly 140,000 images, split halfway between real and fake images. This data set is also already split roughly 71% for training, another 14% for testing, and 14% for validation subsets. And this amounts to a total of 100,000 training images, 20,000 testing images, and another 20,000 validation images.
Yeah, so going into our architecture, we use, like I said earlier, a convolutional neural network. This allows us to be able to pick up more detail from images and capture spatial hierarchies. And it's also highly customizable per situation. Like stated earlier, we resize all the images to 224 by 224 and accept 3 channels, so RGB. And the model itself consists of 5 single convolutional blocks that are very similar, and then a final block that produces the output. So the single convolutional blocks, they look like on the right. So there's 2 convolutions, 2 batch normalizations, and a max pooling. So convolutions are what actually detect the features, such as edges, textures of the specific image. Batch normalization is what standardizes the inputs for the activation functions towards the end of the model and helps stabilize and accelerate training. And max pooling downsamples the feature maps as the sizes continue to change throughout each convolution. It helps make the model more efficient and robust. Finally, after 5 of the single convolutional layer blocks, we have its final block, which consists of flattening 2 dense layers and a dropout. So first it flattens the whole thing into a 1D array. Then it goes through a ReLU activation, a function dense layer, which introduces more non-linearity to the model, which helps improve the results. And then it goes through some dropout, which essentially kills some of the neurons to help better prevent overfitting and improve generalization. And finally, it goes through a sigmoid activation function, which enables the binary classification and gives us that percent chance of if it's AI generated or not. And keep in mind, this model has about 17.5 million trainable parameters. And we use the same architecture for both face classification and image classification.
Yep, so moving on to the experimental results and discussion. So here are the hyperparameters that Antonio was mentioning. For the space classifier model, we use a batch size of 32 in order to strike a balance between stability and memory constraints. Image size was limited to 224 by 224 pixels due to the limited quality of data that we could find consistently with our model and limited computing resources we had. And the epoch was set to 10, giving the convergence of both training and validation losses. Finally, the optimizer was set to Atom as well for the default choice, as it is a default choice and is known for its adaptive learning rates and momentum properties. Same thing with the image classifier model, however, the batch size is 16 in this case. So moving on to the phase classifier model, here are the training loss, accuracy, validation loss, and validation accuracy in table format for the phase classifier model through the 10 epochs. The training accuracy steadily increases with each epoch, as you can see in the second column, reaching 98.82% by the final epoch. And both training and validation losses decrease significantly throughout the training process, indicating effective learning and model convergence. Moving on to the next slide, we can see a similar trend for the image classifier model as well. Once again, here we have the training loss, accuracy, validation loss, and validation accuracy. The training accuracy steadily increases, reaching 95.69% by the final epoch, and both training and validation loss decreases significantly as well. Yep. So the results of the phase classifier model is shown here right now, 98.82% with a validation accuracy of 98.08%. We can see that there is no issue with overfit models as the test accuracy and validation accuracies are close to each other. Along with the test and validation loss is low for both models as well, showing that there's a stable performance on new data. One issue that we can address is the size of the image, 224 by 224. The image sizes are small and may not capture the full depth of the image properly in real life image examples.
All right, so moving on to the conclusion, some of our main challenges and the reason we started this project was because of generative AI and its endless possibilities. We needed to differentiate between artificially intelligent images and real images. So with our two convolutional neural networks, we trained two models to basically detect faces and regular images. Our solution also included a website built using Streamlit and Flask, so users are able to input their own images and provide an output to see if their image is AI generated or real. So what was found? So we were able to create two impressive models that were able to detect AI-generated images. And just for some future work, because our data sets were focused on smaller images, as for the mentioned 224 by 224 pixels, we would want to increase our data set and also have more quality images when training our model. We could also incorporate ensemble techniques for higher accuracy and access to higher computing machines. In addition, for public use, we could also deploy our website and model for the general public to use. And that is our presentation. Thank you so much.
Okay, so I'm going to be doing the demo for our application. Our GitHub page is a good repository or a good README about how to try the training scripts. So there's one of the models, AI face classifier, has part of its data set, so you should be able to run it without any issue. And the requirements are there, as well as we Dockerize the web application and provide scripts to build and run a Docker image, which I will show you a snippet of now. Directions are here and it should work for every system. In this Docker file, as you can see, it's installing dependencies, downloading the models, and exposing the correct ports. So as you can see on our right, here's our AI classification app, and I'll demo some images. So we include some images in the repository. So for example, this AI generated image of a cow with a flying saucer detects its AI and it has a prediction score. It has a prediction score because we use a sigmoid activation function, which is able to provide basically like a prediction score. This is another example of a beach from Australia, a picture I took personally, so I know it's a real image. And this will come up as real, but as you can see, the prediction score is not, so it's at 69. And then if we go to face classifier, we'll do, this is a true AI generated image, right? You can very clearly see. And then when we do this one that looks a little more harder, you can see that the score drops a little bit. It's to 36, so you can see it's like not as sure. And so after doing the Docker run, you can do Docker stop .safe, and you can do -C to stop the image from running and delete it off your system. So thank you.